10.2 is doing hypothesis tests for a population proportion. So it really mimics chapter 9, where the first interval we did was for a proportion, and the second interval we did was for a mean. So 10.2 will be hypothesis testing for a proportion, and 10.3 will be for a mean. And where all the steps are similar, the only difference will be whether we're using our Z or our T. Okay? So it says, now that we're familiar with the language, and we might not be familiar, but at least we've seen it, we can begin conducting the hypothesis test. You will find, similar to chapter 9, that we'll perform different tests depending on whether we're doing it for the mean or the proportion. In this section, we're going to do about proportions. So before we get there, let's fill in this blank. It's the same one. It's a pretty big one. It's statistically significant. Statistically significant. Say that 3 times fast. Statistically significant. And I feel like for a lot of things in this chapter, the name itself kind of gives it away. What's it mean to be significant? Important, you make a difference, that kind of thing, right? And statistically just means a stat. So what we're going to do, guys, is we are going to do these hypothesis tests based on our sample stuff. And if the difference between what we find in our sample and what we think the population is statistically significant, meaning a big enough difference, it's important enough, we're going to be able to reject the null. So it just says, when you observe results that are unlikely under the assumption that the null is true, we say the result's statistically significant. When those are true, we'll reject the null. So basically, you start finding things that are like, you said it was 14 inches long, and my average was like 18 inches. I bet it's not 14. That gap is statistically significant, all right? There's 3 ways, actually there's 3 ways to do hypothesis testing. One was the classical method. It's kind of like the old school method. One was using intervals, but it's only for not equal tests. So it only could be used 1 of the 3 times. The one that we're going to be using, guys, is called the p-value approach. And basically, let's see how good you guys are. I know we don't have to take a final, but do you guys remember what it meant to be unusual? Less than 5%, okay? And that's kind of the idea of the p-value approach. We're going to do this whole test assuming the null is true. The wizard is right. The average length of a horn is 14 inches. And we're going to do all this math, and then we're going to use our sample average of 18 inches or something like that. So basically what we're going to do is if your p-value is really low, that just means that's the odds of you getting your average, assuming that the average was 14, aka unusual. If it's unusual, it means the claim's probably not right, and we'll be able to reject. And the more we do, the more that will make sense, okay? So it just says, you assume the null is true. If the probability of getting your sample mean or sample proportion is extreme more in either direction, either really, really low or really, really big, we're going to reject the null, okay? Before we do the test, guys, we got to remember this. What's the best thing to estimate a population proportion? The sample proportion. So let's not forget about p-hat being our point estimate, right? That's something in chapter 9 we'll be asking you. And these 3 things must be true. The sample is obtained using a simple random sample. I think that's what got tricky on chapter 9. Either they flat out tell you they used a random sample, so you say it was stated, or you have to assume, and you have to say it can be assumed, right? If anybody's done that chapter 9 stuff, they have a drop down about your sampling technique, okay? So it's either stated because it's said in the problem, or you have to assume it. And then the second drop-down menu for chapter 9 is you have to prove that your sample size times your proportion times 1 is greater or equal to 10. They're going to want you to put whatever that number is and say it's greater than 10 or not less than 10. In this guy, I'm not as worried, but again, in words, it just means your sample size is less than 5% of your population size. Last but not least, the sample values are all independent of each other. So let's go ahead and roll this over. These 6 steps that we use in this section are the exact 6 steps we're going to use in 10.3. The only difference is instead of a Z test statistic using proportions, we're going to have a T test statistic using averages. That's the only difference. All the other steps are really the same. I call this my skeleton. Notice it's kind of down here. This is what you'll be given on the test, okay? So all these steps will be like this with blanks for you to fill in. You don't have to memorize the steps. You need to know how to apply the steps, okay? So let's look at number 1. Number 1, determine the null alternative hypotheses. You guys can do that. That's what we did in 10.1, okay? Step number 2, select the level of significance, alpha, based on the seriousness of making a type 1 error. They say select, but notice in parentheses, it's usually just stated. Alpha is this. Guaranteed point, guys. If you don't remember anything, down here where it says what's the level of alpha, go find alpha and fill in that blank. A guaranteed point for you, all right? Step number 3, compute the test statistic. We haven't had to do that yet, so that is new in this section. Step number 4, determine the p-value. Guess what? That's not really new. That's finding the probability of doing this. If it's a left tail or a left tail test, it's the area from your grade sheet. If it's a right tail, what do we have to do? Subtract from 1, okay? Or if it's not equals, we have to look at both tails and double them, okay? So that's not really new. 5 is new. We have to decide whether we reject or not. That's called, let me catch up with you guys, the decision rule. And it sounds really important, like the decision rule. Like it's a big deal. But how you decide is based on your p-value, okay? So again, I'm going to try my best to make it make sense to you what you're doing. But if all else fails, just memorize and mimic, right? But the whole idea is you're going to find the probability of getting your sample mean or your sample proportion is really, really small. That's shady. That's weird. So most likely you're going to reject, okay? So if your p-value is less than alpha, and it says it right here, reject the null when your p-value is less than alpha. Okay, that's what the level of significance is. Reject the null if your p-value is less than alpha. Okay, so you have to memorize that, but I'll try to make sense to you why that is what it is, and hopefully if it makes sense, you're not memorizing it, and you can just perform it. All right, 6, state the conclusion. You know how to do that. That's what we just did in 10.1. If you reject, there is sufficient evidence to support each one. If you do not reject, there's not sufficient evidence, okay? So we've already done 1, you can do 2, we've already done kind of 4, and we've done 6. So the only new things is computing the test statistic. But guys, that is just 8.2. And then 5, deciding whether to reject or not, okay? So let's see what's going on here. It says a researcher claims that more than 55% of U.S. adults watch the news regularly. You asked 425 random adults, and 255 of them say that they watch the news. At alpha equaling 0.05, is there enough evidence to support the researcher's claim? Before we can jump in, we have to make sure this inequality is greater than 10. So what was our n? How many people did we ask? 420. What was our p? What's the supposed proportion? What's the only percent they gave us? 0.55, right? So notice that's why I have n times p times 1 minus p is just our n of 425 times our percentage of 55% times its complement, right? 45%. When you do that math, you get 105.19, which is greater or equal to 10. So that's that check mark, okay? What else do we need to know? We need to know p hat, because you have to know what we're even dealing with, okay? Supposedly more than 55% of people watch the news. What was your sample proportion? Well, I asked 425 and 255 of them say they watch the news. So what was our sample proportion? 60%. So hopefully I can get to at least more than half of you guys. What we're trying to prove is that more than 55% of people watch the news based on our sample proportion of what? 60. Is 60% greater than 55%? Not a trick question. Yes. But the question is that 5% gap a big enough difference, or is it just a gap because we sampled? We didn't ask everyone, okay? So that's the whole point of hypothesis testing, is you're going to get a sample, and you're wondering, is that sample off because we just sampled, or off because really more than 55% of people watch the news? So let's state our hypotheses, the null and the alternative. What symbol are we going to use? P, because we're dealing with proportions. What sign does the null hypothesis always have? Equal. And what are we trying to prove in this case? Greater than. Greater than what? 55%. So that means somewhere out there someone thought it was 55%. So this is what type of test? Right tail. The reason why I'm making note of that is when we go to find our probability, guys, we're looking at the right tail, so we're going to subtract from 1 or use the symmetry rule. That's the only reason why, if you don't do that on a test, that's fine. I'm just kind of making a mental note. Okay, we're going to be in the right tail. All right, what's the level of significance? 0.05, right? What does that mean? It means I have a 5% chance of rejecting the null when I shouldn't. It's the probability of making a type 1 error. So I have a 5% chance of saying reject when I shouldn't, okay? So what we're going to do is we're going to compute the test statistic using this formula of above. Let's see if we can make sense of everything. What's p hat stand for? What is p hat? 0.6, but what is that? That's our sample proportion. What do you think p naught is? Nope. P naught, here, let's label all this. Okay, so this is your sample proportion. That way, when you go to put them in, you put them in the right spots. Okay, so P hat's your sample proportion. What did you find? P naught is your hypothesized proportion. In this case, what is that? 55%. Is that okay? We use, this would be a big parenthesis there. We use P naught here, here, and here, and then what does N stand for? Sample size. And I know a whole lot of us didn't do the greatest on 8.2, but this is exactly 8.2. You take your sample proportion, you put them in front, you subtract the supposed mean or supposed proportion, and then you divide by the standard deviation, and that's what we're doing, okay? So remember, try to stay exact as possible, so like don't really round until the very end. So we're going to do z equals p hat minus p over p times 1 minus p all over n. And I'm writing the generic, that way you just know where things are going. I don't put the little knot because I just know it's my p, my population proportion. So I don't worry about the little knot. And I'm just going to fill in what I know. I've basically labeled everything already. P was the 55%. P hat's what they calculated, the 60%, or you could calculate that 255 over 425. And then your n's the 425. So we're just going to fill everything in. So we have 60% minus 55% all over 55%, 1 minus 55% all over 425. So remember, order of operations, do the difference on top first, and do that crazy calculation to lots of decimals. Okay? So round to like 4 decimals, okay? You should be good. Will you guys make sure you can get the standard deviation there? So we're going to take 55% times the complement of 55% all over 425, and then take the square root. So rounded to 4 decimals, you should get 0.0241. Does that look right? You guys get that? Okay. So remember, when we're talking about proportions, your standard deviation is kind of like your margin of error, give or take 2.4%, right? So the question is that gap of 5% compared to your standard deviation of 2.4% a big enough gap, all right? So when we divide these two, it's a z-score. Do you remember how many decimals we round z-scores to? 2. Do you guys get 2.07? All right? So number 3 is basically just calculating your z-score like you did in 8.2. And then number 4 is just calculating the probability of a right-tailed test with that z-score. So what are we going to do with 2.07? We're going to grab our gray sheet and either look at its inverse, negative 2.07, or I look at 2.07 and subtract it from what number? 1. So since this was right-tailed, right, I'm reminding myself again, I'm doing 1 minus, what is it, 9808? So my p-value is 0.0192. Here's my z. So really labeling it right or left tail, guys, based on greater than or less than, just helps you with your p-value to remind yourself what you need to do in order to find that area. Okay, so nothing new so far, right? Number 1 was 10.1. Number 2, you're just grabbing from the sentence. Number 3 and 4 is just really section 8.2. The only new thing is number 5. How do we know whether to reject or not? And guys, every semester, This is like my Christmas wish list, all right? Like, I will make it make sense to someone in the class why the rule is what it is. But even if it doesn't make sense, you just memorize what you have to do, okay? So we're going to go back to number 5 up top and just read what it says. It says, reject your null hypothesis if your p-value is less than your level of significance. What was our level of significance? 5%. What's our p-value?
55.
Nope. Okay, so that's going to get confusing, right? So she's thinking p, our population proportion, but p-value is 0.0192. So is this less than our alpha? Yes. So we will check. Let's write that first, but I'm going to explain my darnest why that is, okay? So we're going to reject H naught since p-value is less than alpha. And our p-value is 0.05, and that's less than 0.0192. I'm just putting it in numbers so you can see what we're doing. We're going to reject the null since our p-value, oops, I flip-flopped it, sorry. Anybody question that? Eek, erase that. Our p-value is the 0.0192. That's less than our alpha of 0.05. I'm sorry about that, guys. I'm glad I caught that before I had you study off of that. All right, so if it doesn't make sense, just memorize it. If your p-value is really, really small, how small, alpha is your measurement, you're going to reject, all right? Why that is, and again, like, I'm going to do it today, I'm going to do it Wednesday, I'm going to do it Thursday or Tuesday next week when we're reviewing. Why it is because this is the probability of getting a sample proportion of 60%, assuming the average was 55%. So, according to this, if the average was really 55%, we had less than a 2% chance of getting our sample of 60%. But are we bad at sampling? Heck no, we're not bad at sampling. We're good. Our sample proportion of 60% is a good estimate. So where is the error? The error is in assuming that it's 55%. AKA, guys, if this was really 55%, it would have been unusual if we got a 60% sample proportion. But we got a sample of 60% proportion. So guess what? We can reject the null. And you don't have to do this, but I kind of do it lightly. If you can reject the null, what does that mean? As far as our conclusion goes, there is or is not sufficient evidence. Which one is it going to be? There is sufficient evidence to support H1. There is sufficient evidence to support H1. What does that mean? It means that sample proportion of 60% that we found was a big enough gap. It was far away enough from 55% to say, you know what, the average is actually more. It's probably close. Do we know what the average is? No, we just know it's more than 55%, probably closer to our sample proportion of 60%, okay? So again, I'm going to try to make this make sense. The reason why we reject the null is because it was really unlikely to get our sample proportion if the null was true, but we got our sample proportion. We didn't mess up. The proportion's probably closer to 60%. So, since that was so unlikely, that's probably unlikely, okay? So we're going to reject it. Are there any questions on, and this is going to be iffy, so I'm sure we have questions on that, but are there any questions on 3, 4, or 6? 5 you can still question, it's allowed, okay? 3, 4, and 6, let me know if I can clarify anything there. If you don't have any questions, go ahead and flip it to number 7, or excuse me, page 7. What we're going to look at is another example using hypothesis testing to test a claim, okay? So, let's see what's going on here. It says, Harper's Index claims that 23% of U.S. citizens are in favor of banning cigarettes. So what can we label that? That is P. That's the supposed proportion of people that are in favor of banning cigarettes. 200 people are sampled. So what can we label 200 as? N. Kind of hard to notice because it's in words, not numbers, right? And 27 are in favor of the ban. So what can we label 27% as? Not X, because it's a percent. So what can we label it with? P hat. Every percent you should be able to label P, the supposed proportion, or P hat, the sample proportion. We took our sample and found that 27% were in favor of the ban. So this is one that you didn't have to calculate it. It was just handed to you. 200 people were asked, 27 want to get rid of cigarettes. At alpha equaling 0.05, is there enough evidence to prove that the population proportion is different than 23%? Okay, so that will tell us what symbol we're going to use when we do our hypotheses. So looking at the first things, we have to make sure this is approximately normal. So our N was 200, so that's why he goes there. Our P, our supposed proportion, is 23%, so that's why he goes there. And 1 minus that's just 0.77. If you multiply all that, guys, you get 35.42, which is greater than or equal to 10. And then P hat, we didn't have to find. We know it's 27%. So let's go ahead and state our hypotheses, the null and the alternative. What symbol are we going to use? P or mu? P, because we're dealing with percents. What symbol does the null always have? Equal. And what are we trying to prove with our alternative? Is different, so is not equal. What p-value will we use, 23 or 27? 23, because remember, that's the claim. You're always trying to question what was stated in the beginning, so we're trying to prove it's different than 23%. So really the question is that 4% difference big enough to say yes it is or no it's not, all right? Your level of significance, it's stated. What is our level of significance? 5%, meaning we have a 5% chance of saying reject when we shouldn't. The test statistic, we're dealing with P's, proportion, so I'm going to grab that from my formula sheet. P hat minus P all over the square root of P times 1 minus P all over N. Okay? And that's just from your formula sheet. So remember on your test, you'll have a formula sheet for your test statistics. It will be Z's with P's, and it will be T's with mu's, just like your confidence intervals. All right, let's fill in what we know. What was our sample proportion? 27. Minus our supposed proportion of 23 over 23 times 1 minus 0.23 over N. And I forgot to say this was two-tailed, sorry.
N is 200.
Oh, yeah, but I want to put that in there, not just N, 200. All right, do your difference on top, so we can do that pretty easily. That's the 4%. But remember, lots of decimals, use like 4 decimals to do 4 or 5, really. I did 4 in my notes. When you do that, you should get 0.23 times 1 minus 0.23 divided by 200 and do the square root of all that. I got 0.0298. Does that look okay? So, again, when you divide these two, you will be finding the z-score. And z-scores are rounded to 2 decimals. So when you divide the two, you should get 1.34. Is that okay so far, guys? And even if you're not having a chance to like calculate it, it's okay where the numbers are coming from, okay? So this is what's kind of a little awkward. And guys, once we get done with this, I'm going to show you, guess what I have? A blue sheet. What does that mean? We can do stuff on our calculator, okay? So this one's a little awkward to do by hand. Your calculator takes care of it for you. A two-tailed test means we don't even care that the 27 was higher. We want to worry about both tails, okay? So we want to worry about less than negative 1.34 and more than positive 1.34. So a two-tailed test is kind of weird. You have to think about both tails. So where was ours? Ours is over here. He's positive, so he would be considered our right tail. But since it's not equal, we want left and right, so we got to do the left one too. Okay? And that's true even if that was a negative 1.34. Okay? So even if this was a negative 1.34, you'd have to consider him and the positive 1.34. So of these two tails, which one's easier to calculate? Of those two tails, which one's easier to calculate?
Negative.
The negative. Why? Because it's on the left side. So what we can do, guys, is we can just go look up negative 1.34 and see what his area is. But guess what? That will be his area too. So you can either add them together or just double it, okay? So if you look at your gray sheet, so look up negative 1.34. I got an area of, was it 0.0901? Does that look right? And then times 2, because it's two-tailed test, your p-value is actually 1802. And again, you might ask yourself, so what? What does that mean? It just means if the proportion of people that wanted to ban cigarettes was really 23, that is the biggest bug up there. What is that thing? Giant. It's not on here. That's up there. That's big. If the proportion of people that wanted to ban cigarettes was really 23%, we had about an 18% chance of getting our proportion of 27. Is 18 that weird? No. I mean, it's kind of low, but it's not lower than our alpha, okay? So determine whether to reject the null. This is not less than our alpha, so we do not reject. Do not reject H naught. Since our p-value is greater than alpha, right? So 0.1802 is greater than our alpha 0.05, meaning it's not that weird. It's not that shady. 23 could be our real percent, okay? We had an 18% chance of getting our proportion of 27. Not the most likely, but not that unlikely. And that's the whole idea. Does that make sense to anyone? Kind of, okay? Like I said, even if it doesn't, just remember, really low, something weird's going on, we probably need to get rid of that claim, okay? Really low, something weird's going on. How low? Your alpha. It just so happens that both of these alphas were 0.05, but they may vary from 0.1 to 0.01, okay? So you're always comparing to alpha. All right, so what's our conclusion? Since we do not reject, there is not sufficient evidence to support H1. There is not sufficient evidence to support H1.
What happens if your p-value is equal to alpha?
It has to be less than alpha. So if it's equal to alpha, you still can't reject, okay? And that sometimes happens. There is not sufficient evidence, so it's a strict inequality. There's not sufficient evidence to support H1. Meaning, based on our status, we can't prove him. Does that mean it is 23%? No. It just means we don't have enough to prove 23%. Okay?